Okay, so today's video is going to look at extending our confidence interval idea to now go into our hypothesis test for means. Um, and this is going to be what's known as our one sample t-test. Now there is also a one sample z-test, and the same ideas would go back to hold. The main question we talk about when we talk about means is, do we know sigma? Remember, sigma stands for our population standard deviation. Typically, we do not know this value, and if we don't know sigma, we replace it with S. And as soon as I do that, that creates extra variability. That extra variability in my estimates leads us to using the t-distribution. And so that's why you will see that this is a one sample t-test, because we're going to be using the t-distribution. So out is the normal distribution. Now, if I did know sigma, and I use that throughout, I could use Z, but we are not going to really do that much in AP statistics, okay? In the real world, there's lots of times that they do still use Z, but again, for our world, we're just going to make it a little bit easier. If we don't know sigma, we're going to replace it with S, the sample standard deviation, and that extra variability creates this need for a new distribution, okay? So, as we do with any hypothesis test, we're going to follow our regular steps of just phantoms to help us out. Now, again, our P is going to be our parameter. What are we interested in? Now make sure you understand, a parameter in this case is now going to be mu, because we're talking about means. Never state it as a statistic, right? We know what X bar is. I don't need to try to figure that out. I don't know what mu is. That's what we're trying to estimate, okay? Or in this case, what we're claiming and testing, okay? Our HO will be that mu equals some value, and my alternative, just like before, will be mu is either different, less than, or greater than. So again, if you set these up between your HO and your HA, you'll see the same parameter here. Before it was P's or pi's, right? It's always going to, let's just say, equals, let's say like 98.6, and let's say that it doesn't equal 98.6. So let's just say we're talking about temperature, right? Notice again some similarities here. Mu, the value's the same. The only thing that should really change is we'll have an equals to begin and a not equal to or less than or an inequality for the alternative, okay? Conditions are the same as before. Number one, it's randomized. We need random assignments or random sample. We either sample with replacement or 10 times the sample size. Or finally, our normality / large sample size condition, which is the same one we looked at for confidence intervals. Now, I did add in a little extra asterisk here, just for your knowledge and questions you might get asked on multiple choice. But in order to use the t-distribution, the underlying assumption is that the population is normally distributed. That's what we hope. But fortunately, the t-distribution is what's called robust, which means that the capture rate will be close to the confidence level or the value that we state, even if the population isn't perfectly normal, except if there are outliers or strong skewness with small sample sizes. So this key phrase, robust, is something that you will see. Again, we'll get more of a chance to talk about that. Now, larger samples, though, improve the accuracy of these critical values of the t-distribution, and that's important. It's really when we're talking about small sample size, and that's why we keep coming back to that n is less than 30 p's. Okay? Name one sample t-test. Our test statistic is this new formula here. We take our sample mean, x bar, minus the population mean, mu, divided by S over the square root of n. And again, the key thing is going to be in here your degrees of freedom, because that's going to determine which curve that you're in. Okay? Our p-value will be the area beyond it, and we'll use technology to help us figure that out, make a decision of whether to reject or fail to reject, and state the conclusion in context. Okay, so we got all that stuff so far. So let's just say for each of these, in each of these cases, they're going to give us an alpha level. Now remember, that's our significance level. That's how much evidence do we need to reject the HO, right? So our significance level. They're going to give us a t-test statistic and a sample size. And what we want to determine is, would we reject or fail to reject the HO? So basically, they're asking us to figure out the p-value. Okay, so first, n is 15. So that means my degrees of freedom would be 14. So let's first draw a t-distribution. Okay, a t-distribution is going to look exactly like a normal distribution. There's going to be a couple of differences. It's probably going to be a little bit lower. It's going to have a little bit fatter of tails, because we're going to expect more values further away. But it'll be centered at 0, just like our standard normal curve, right? And this would be like a t-score of 1, and this would be like a t-score of 2, right? And so it just basically follows like a normal distribution. When you draw, you're just going to basically draw it the same, but you're going to know in your head that it has fatter tails. Okay, so my test statistic, t, is 1.54, which would fall somewhere right in here. So now the question is, which way do I need to shade? And because it says t is greater than 1.54, I'm going to shade everything to the right. Now, I need this area under the curve. Now, most people might say, hey, go look at your normal distribution sheet. But this thing is not normal. It's the t-distribution. So here's the problem. Our t-distribution sheet that you have is actually kind of an abbreviated one. So I'm going to use technology to help me out. I'm going to go to rossmanchance.com. You guys know I love this site. And if I go over here to the t probability calculator, it'll bring up a cool little applet. So I'm going to go ahead and put in my degrees of freedom, 14. And so you can actually see, did you see how it changed? See how the t with 1 degree of freedom is different than 14 degrees of freedom? And if I went to like 1,000 degrees of freedom, or 100, you'd see that it's even more different. Well, actually, it didn't change that much because it's getting pretty close. But we can see that it's a little bit different. So there's 14 degrees of freedom. Now, I want to find my t-value was 1.54. And I want to find the area above that. So if I click this, it'll change it to greater than. Look, there's my shaded area. And we can see that that probability is 0.07. So this right here is actually my p-value. So the p-value is 0.073. So the p-value is 0.073. Okay, so then it asks us to make a decision. Would we reject or fail to reject? What was alpha? 0.05. So 0.073 is greater than 0.05. Remember, my p-value is greater than alpha. We fail to reject HO. And again, remember, this area right in here is my p-value. Okay, so there's the first one. Let's try the next one. Alpha is 0.1. That doesn't matter except for our decision. T is negative 1.37, N is 20. Okay, so we grab our degrees of freedom, which would be 19. Okay, let's draw a curve. Now this will be even more normal than the previous one. Here's a t-score of 0. Here's negative 1. And here's negative 2. Okay, so I'm going to go to negative 1.37, somewhere in here. And I'm now going to shade everything to the left this time because it says t is less than. So this area right in here is my p-value. Okay, so I need to use some technology to help me figure that out. So again, I'm going to come back here, 19 degrees of freedom. I'm now going to switch this to being less than negative 1.37, I believe is what it was. Yep. And now my p-value is 0.0933. And what do we notice about that p-value? It is 0.0933 is less than 0.10, so what would my decision be? Reject HO. Okay. Last one. Alpha is 0.01. Now t is not equal 3.14. Now remember how this works. Okay? So we come here in the middle. We go to 3.14. I find everything above that. Because it's not equal to, though, I also go to negative 3.14. And I find everything below that. And so I have two options here. And don't forget my degrees of freedom are 54 here. So when I come back to my probability calculator, we got 54 degrees of freedom. We're going to go, what was it, 3.14. All right, and we want to find greater than that on one end, which is tiny. And then I'm going to also add in negative 3.14. Now, you might be sitting there saying at home, hey, wait a second. Couldn't we just have taken this one and doubled it? And you'd be exactly right. So the p-value, the probability outside, see that of the outside, is 0.0027. And that's the p-value in this case, 0.0027. Which is obviously less than 0.01. So my decision then would be to reject HO. All right, you're not limited to just doing this on a calculator. Let's actually go back and look at the first one that we did, greater than 1.54. If you have a TI Inspire at home, which you actually have as of recording this today, you have the ability to download that software for free. I will push that out to you so you can get this at home on your computer. But it's just like norm CDF. So you'd go menu, probability, distributions, and if you go to a TCDF function, which is right there, you now just fill in your values. So our lower bound was 1.54. I'm going back to the first one. My upper bound was something like infinity. And then degrees of freedom is so important because you have to make sure you specify which curve you're in. And 14, and there you go, 0.0729. That is my p-value, 0.073, which is what we got off the computer. Okay, so we can do that. Now here's the lovely thing, is that the calculator will really do all of this for us. Alright, so now we understand how to get p-values with this t-distribution. Let's go ahead and run through a whole test. Okay, so mass of a large bag of fries. So to estimate the average mass of a large bag of French fries at McDonald's, a class bought 30 bags of fries during 2 different half-hour periods on 2 consecutive days at the same McDonald's, and they weighed the fries. Let's assume that they randomly picked the times. So McDonald's advertises that the mass of a large order of fries is 171 grams. Is there evidence that McDonald's is underfilling the bag of fries? Okay. So this is asking us for evidence at this point. That's telling us that we want to do a hypothesis test. Okay, so it didn't say estimate it. It says give me evidence. This is a yes or no question. Okay, so I'm going to walk through all the steps of phantoms just to help us out. So we're going to begin with defining my parameter of interest. Okay, we're interested in the mass of a large bag of fries. Now, not just of one bag, of all of the bags. So we want to figure out what is mu. So mu is the true mean, right? Weight or mass, true mean mass of a large order of fries. And now what's my sample from? It's from this McDonald's. So I can only generalize to this McDonald's. From this McDonald's. And we're just going to do Mickey D's. Alright, so there we go. So there's my parameter of interest. So now we're going to come and grab our hypotheses. Okay, so I'm going to have 2 hypotheses here. We're going to have a HO colon, HA colon. So what did McDonald's claim that it was? McDonald's claimed that it was 171 grams. Okay? We're trying to prove that they're underfilling. So that means that mu would be less than 171 grams. So that's what we want to go ahead and try to prove, that mu is less than 171 grams. Okay, let's keep rolling here. So now we need to assess our conditions. Okay, so we have 3 conditions. Number 1, we're going to have to assume that this was a random sample of times. So we'll assume randomly selected times. Right? There is going to be more than 10 times 30, 300 possible fries, 300 possible bags of fries. Okay, condition number 3. This is our normality / large sample size. And what do we notice? What was the sample size? 30. So does that count as a large sample size? You got it. So 30 is greater than or equal to 30, so we can use the t-distribution. And again, this comes back to our central limit theorem kicking in. So the sampling distribution would be approximately normal. Is approximately normal. Okay, so my conditions are met. So now we're going to go ahead and name the test. Alright, so we're going to go ahead and name this thing. So this is a 1 sample t-test. Why is it 1 sample t-test? Well, how many samples do I have? 1. Which distribution do I have to use? T. Because I don't know sigma. Okay? Alright, so now we're going to go ahead and write our test statistic. So our test statistic looks like this. I know it says t here for test statistic, but you have to put t equals, because it's a t-score. It's x bar minus mu, s over the square root of n. Now remember, I wrote t, so I also need my degrees of freedom. Sample size minus 1, which would be 29. Okay? So now I need to go grab my sample mean and the standard deviation, and I need to calculate my test statistic. Okay, so I'm going to come to my calculator here. I've already typed these in, and I'll show you ways to do this if you're at home and you don't have your calculator. So menu, stat, and I'm going to do it the long way first. 1 var stats, just to remember that. 1 list, and it's just going to run it on fries. So this is the long way. Okay, so x bar is 144, s is 12.3. So 144 and 12.3. So 144 minus 171, 12.3 over the square root of 30. Okay, I have to go calculate this. Okay, so I plugged that in, and I got negative 12.1. yeah, 12.1, 12.01. Yeah, basically negative 12. Okay, so what does that mean, right? If we come and look at this, here's my t-distribution with 29 degrees of freedom. Remember, it'd be centered at 0. It's just like a z-score. This is a t-score. It's just like a z-score. It's negative 12 standard errors below. I mean, how often have we seen values like negative 12? Almost never, right? Okay. Now, it will be more common in t, again, because we expect things further away. But still, 12 standard errors below. That's crazy. Okay, so I need to go grab my p-value. And again, I'm going to show you the long way here, and then we'll come back and show you the fast way. So if I go with 29 degrees of freedom, and I get rid of this one, and we do less than negative 12, my p-value is basically 0. Alright, so we can see that's way over here, so far away. So its p-value is basically 0. So the p-value is 0. Okay. Wow. So that means it's almost impossible to get this sample mean if it was 171 grams. Does that make sense, though? Look how far away 144 is from 171. It's a long way away. Okay, so now we make a decision. Now, did they give us an alpha level? I don't think they did, so let's use 0.05. But what do we know? 0 is less than 0.05. And so my p-value is less than the alpha. So therefore, my decision would be to reject HO. And what could I say at the end? We have statistically significant evidence. Significant evidence to say that the true mean weight of French fries at this McDonald's is less than 171 grams. And there we go. Alright, so I have evidence, and I could maybe go sue them now. Who knows? You know, there's lots of stuff that ties into this, but it does appear to be like false advertising. Okay, so what are some other ways that I can go and grab my p-value? Alright, and make my life a lot easier. So let's go through first. If you go to rossmanchance.com, okay, so if you come here and you go to that theory-based inference, the same applet that I showed you last time, down here at the bottom. If I go to one mean, because that's what I have, and I paste or type in the data, whatever, it doesn't really matter, but here's all the fries, and I click use data. Notice, it gives me n, it gives me x bar, it gives me s, and hey, look at this graph. Pretty symmetric and mound shape. So actually, even if I didn't have a large sample size, I would still be good with using my t-distribution, right? Because there's no skewness or outliers, so we're good. So if I come over here now and click test of significance, and I now put in my mu, so 171 was our HO, and we want to prove that it was less than 171, and if you click calculate, it does everything for you. Here's my test statistic, and here's my p-value. And the great thing at the end is you can even run a confidence interval at the end and say, hey, look, we actually believe it's somewhere between 139 and 148, which is very strong evidence against 171. What about if you have a TI Inspire? Alright, so what if you have a TI Inspire at home? Now I showed you the long way before, so I'm just going to delete that out. But in the first blank column, first blank row, I can actually just run the hypothesis test. So if in my data is in there, menu, stat tests, and if I just go to a t-test, it's right there. And I have the data, so I leave it. If I just had the x bar and s and n, I would go to stats, but I have the data. Mu naught, so that's my HO, 171. What list did you have the data in? I typed mine in as fries. We want to prove that it was less than. And then once you have everything there, just hit OK. And look, there's my test statistic, p-value. Now remember, if you see p-value like this, that basically means 0. That's 12 zeros and then 4. Okay? X bar, S, N. So again, the mechanics of this thing really shouldn't be too tough. Alright? Let's go ahead and try one more. I'm going to skip this next one. We're going to jump to the number 3 here. So ancient Greeks used this golden ratio. Maybe you guys have used golden ratio in art or photography or anything like that. But basically it talks about the width to length ratio being around 0.618. Alright? And they just believe that that number is visually pleasing. So some have conjectured that American Indians also used the exact same ratio. So the following width to length ratios for a sample of 20 beaded rectangles used by the Shoshone Indians to decorate their leather goods. So here are all of the ratios that we have. Now these are ratios, but they are quantitative. We can average these together. So first we're talking about means. Okay. the question is, do we know sigma? Did they give us the population standard deviation of all of these beaded rectangles ever made? And the answer is no. So we're going to replace sigma with S, the sample standard deviation of these 20, which tells me we're in that T-distribution. Okay? Alright, so anyways, let's go ahead and walk through this whole thing. So my parameter of interest is going to be mu is the true mean width to length ratio of all beaded rectangles used by the Shoshone. And I'm kind of just going a little bit short here, but just to save some time on the video. Okay, so let's go ahead and check our hypotheses. Now, our HO, right, what are we going to start off by assuming? That it is 0.618. Remember, we always start off by assuming that. And my HA is just some have conjectured they use the same ratio, and we just want to figure out, is it the same or is it not the same? So my HA would be mu does not equal 0.618. Okay, so again, we see the same value, same parameter, equal, not equal to. Now this is leading us up for a two-tailed test, right? Okay, let's go ahead and assess our conditions. So number one, we were told it was a random sample. Remember, that provides us with unbiased estimators. Okay, number two, we know that there's more than 10 times sample size. 10 times 20, 200 possible rectangles. Okay, third condition, normality / large sample size. All right, so we're here. We need to go graph this thing. So 20 is not bigger than 30, so I have to go and graph it. Now I've already typed this in just to make my life a little bit easier. In order to graph this, we're going to add a page, and I can do dot plots. Okay, so here's the golden ratio. Oh, okay, so it looks like a little bit skewed to the right, doesn't it? Let's look at a normal probability plot. Yeah, it definitely looks slightly skewed. Okay, but here's the deal. Oh man, I'm going to look also at a box plot. Okay, so yeah, it definitely looks skewed and with a couple of outliers, doesn't it? So what we're going to do here is they asked us to build this one. So I'm gonna say that we're going to proceed with caution here on this one, and I'm just going to mention it. So just so you're aware, we're never going to try to really throw you off here on these types of questions. But what we're going to do is we're going to say, hey, this looks like it shows some deviations away from normal. Okay, so it looks like it shows some deviations away from normal. But the T-distribution is robust. As my sample size gets closer to 30, these deviations don't really matter as much. Okay, so I'm just going to kind of mention that, and I'm just going to kind of use this phrase called proceed with caution. All right, and it just kind of lets us, because what did they ask us to do? They asked us to make the graph, right? Or they asked us to do the hypothesis test. So I'm going to do the hypothesis test. I'm just going to say maybe my conditions aren't met. Okay, so the normal probability plot shows a skewed right distribution with 2 outliers. Okay, so what I'm going to say is, so we will proceed, so we want the data to be symmetric with no outliers. So we'll proceed with caution. Alright, and so basically what we're saying is, I don't think this condition is quite met. And therefore my analysis might not be right, but I'm just going to proceed because you asked me to kind of go through all the work. And again, we're never going to try to trick you about this stuff, but this is part of that T-distribution being robust. So as n gets bigger, it's closer to 30, I'm okay with some skewness and outliers because it's probably going to be alright. But again, we'd have to come back and do a little more analysis, and that's not the point of this video right now. Alright, so let's go ahead and keep rolling with this thing. So we're going to name the test. So this is going to be our one sample t-test. Okay, anytime I put t, I put my degrees of freedom, which would be 19 in this case. Okay, my test statistic, I have to put t equals. Now let's show the formula. X bar minus mu s over the square root of n. Now if I knew sigma, it'd be z, but it's not. Okay, I need to go grab x bar and s, and actually that's all done in the normal probability plot. So it's 0.66 minus 0.618 divided by s, and again all this is right here, and I'm going to show us how to grab this again in a second. 0.102 divided by the square root of 20. Alright, so now from here, I'm going to make my life way easier, and I'm just going to go calculate our test statistic and p-value. So I'm going to come back here. So first blank column, first blank row, menu, stat test, t-test. And again, I have the data, so I hit OK. 0.618 was my HO. My list is golden, and we just wanted not equal to. Okay, so there we go, and we hit OK. There's my t-test statistic and my p-value. So 1.99. And I'm going to draw a quick little picture here because this is t, here's 0, here's 1.99. I shade above that. Because it's two-sided, I also do below negative 1.99, but the calculator does all of this for us. My p-value was 0.061, and they did not give us an alpha level again, so I'm going to use the alpha of 0.1 this time. Actually, no, I'm not. I'm going to use 0.05. Okay, so we use 0.05. So what do we notice? 0.061 is greater than 0.05, so my p-value is greater than alpha, so therefore we're going to fail to reject HO. In this case, we do not have evidence to say the true mean width to length ratio for the rectangles by the Shoshone Indians is different than 0.618. So I just can't say that it's different, okay? Remember, that's my HA that comes back there. Alright, so that's pretty much all that. Let's say that you were at home and you, again, don't have the calculator. Again, I'll show you how to do this one more time in Rossmann-Chance. So again, you go to theory-based inference, right here. Click paste data. We want one mean, obviously, because we're dealing with means. Delete it out. Paste it in there. Click use data. N, X bar, S, test of significance over here. And again, you see your graph there. We can see it's skewed to the right. 0.618 and not equal to 0.618. If you click it twice, it'll get you that. And calculate. Oh, and they give me a slightly different p-value. Maybe, maybe rounding or something. Not quite sure what that's up with, but still the same decision, 0.058. All right, so that is all of those. The other ones that you have left to work on are a little bit easier. You have two left you have to do, but like 5, it gives you X bar S. So when you put these ones in the calculator, you'd use the stats because they just give you the stats. So they don't tell you, they don't give you all the individual values. So that makes life a little bit easier. All right, well, I hope that was helpful. Catch up with you guys soon.